Welcome to this Global Climate Change Week. I'm going to read out the blurb on the website of what Global Climate Change Week is, just in case you're not aware. So the Global Climate Change Week encourages universities and their communities across all disciplines and countries to engage with each other, their communities and policymakers on climate change action and solutions. Held annually in October, the Global Climate Change Week provides an open-ended framework for voluntary activities aimed at raising awareness, inspiring behavior change, and driving political transformation in relation to climate policy. So the Center for Environmental Informatics, which Bao was a student in for the past 4 years, we do a lot of work on the environment and climate. And so we've been hosting these seminars regularly for a number of years now. We're very happy today to have Bao Anh Vu. I'll give a brief introduction to Bao. So Bao recently completed her PhD in applied statistics at the University of Wollongong, and she's now Associate Research Fellow in the School of Mathematics and Applied Statistics at UOW. Her research lies at the intersection of Bayesian statistical inference and glaciology. Her PhD project is part of Securing Antarctica's Environmental Future, or SAFE. SAFE is an Australian Research Council's special research initiative for understanding, forecasting, and managing changes in the Antarctic region. Bao's work was nominated for the Statistical Society of Australia's J.B. Douglas Award, and she received a prize for Best Student Presentation at the International Environmetric Society Conference in 2024. Should also say that Bao will be joining ANU from December this year, right? With a really good statistics group over there, and we're very happy for her. Okay, so we can now proceed with her talk, which is titled "Estimating Antarctic Subglacial Conditions with Deep Learning."
Thank you, Andrew, for the introduction. Welcome, everybody, and thanks for coming along to my talk. I am going to show you a piece of work that I've been working on for a couple of years now. And what I will be able to show you in the next 45 minutes is really just the tip of the iceberg, if you will excuse the pun. So if anything, I hope you come away from this talk with a sense of appreciation for all the work that's being done on the Antarctic continent to understand what's happening, the changes that are happening there. So this work is part of, again, Securing Antarctica's Environmental Future, which is a special research initiative from the Australian Research Council. I also want to thank my collaborators, who are 3 fantastic statisticians from the University of Wollongong, meaning Andrew, who you've just heard from, David and Noel, who are in the audience today. And I also want to thank Felicity McCormack, who is a glaciologist and mathematician at Monash University. I'm grateful for all of their support throughout this project. Right, so I'm going to begin with the impact of melting ice sheets. So Antarctica is the largest freshwater reservoir on Earth and a major contributor to sea level rise. It has the potential to raise sea level by 60 meters if melted in its entirety. To give you an idea of what that looks like, I'm just gonna try again. To give you an idea of what that looks like, this is a map of the Illawarra if sea level were to rise by 60 meters. That means most of the coastline, and then also the campus that we're currently on, is going to be under tide line. But you're gonna tell me I'm being dramatic, right? It's not like the Antarctic ice sheet is going to melt completely. And I hope you're right. So current sea level rise projections from the IPCC report in 2021 shows that we are, in the worst case scenario, going to get around a meter of sea level rise by the end of this century. Okay, now this plot shows you the contribution to sea level rise from different ice sheets and glaciers. So a major portion of the sea level rise, the predicted sea level rise, comes from the Antarctic ice sheet, and another portion comes from the Greenland ice sheet and other glaciers, and also from the ocean thermal expansion. And this is assuming the worst case scenario where we have a lot of greenhouse gas emissions and the temperature raises by a couple of degrees. Okay, the issue we're facing is that the Antarctic ice sheet's contribution is actually quite uncertain. So current model projections disagree a lot on how much the actual contribution from the Antarctic ice sheet is going to be. Here it's showing about 12 centimeters of contribution, but this is actually quite an uncertain estimate. And we're uncertain because the response of the ice sheet to climate change is complex and not well captured by current models. Now, what are the impacts of sea level rise? Well, the number of people per country living on land that is expected to be under sea level by the end of this century is represented in this plot. Now, this is assuming a rise in sea level of 50 to 70 centimeters, so a bit less than the worst case scenario. And you can see that sea level rise is going to impact Asia quite badly, not only because of the population density of Asia, but also because many cities in Asia are in low-lying areas, which are not very high above current sea levels. The next badly impacted areas are the US East Coast and also areas in Europe, namely the Netherlands and Germany. Okay, and it's also not just about the rise in sea level, because every 1 centimeter of sea level rise has the potential to correspond to a meter retreat of the coastline. So it's not just about the water rising, it's also about the coastline disappearing. And so on the right-hand side here, you see a picture of I think this is the Cronulla coastline, eroding because of sea level rising. And with coastal flooding and erosion comes all of the associated economic and social and cultural impacts and loss of habitat along the coast and loss of biodiversity. So I think that goes to show that reducing uncertainty in sea level rise estimates is essential for planning and adaptation all over the world. Now, Antarctic scientists have worked over many decades to develop ice sheet models, mathematical models that try to capture the dynamics of ice and predict how much it flows into the ocean. On the left-hand side here, you see an image of part of the Antarctic ice sheet and a glacier outlet. If we were to take a point in the glacier, in the interior of the glacier, and then follow the ice as it flows to this outlet, and we plot the profile of the ice sheet, the cross-section of the ice sheet, along that line is going to give us a plot like the one that you see on the right-hand side. Okay. Now, I want to point out a number of quantities that we're interested in modeling the ice dynamics. So we need to know, for example, the surface elevation of the ice relative to sea level. So that's how high the ice is, let's say, to the ocean surface. And generally, we consider sea level like zero. We also need to know the bed elevation. So this ice sheet is resting on some underlying bedrock, and we need to know how high this bed is relative to sea level. Usually it's under sea level, so it will be like negative 500, for example, 500 meters below sea level in certain areas, and maybe higher in some places and lower in others. We also need to know, for example, how fast the ice is flowing, that's the velocity of ice. We need to know how much snow is accumulated at the surface, so how much extra snow are we getting every year. And then we also need to know, for example, how much ice is melting at the base. Right, all of these quantities come together in mathematical equations, like the one that you see below. This is a one-dimensional shallow shelf approximation model. One-dimensional because it's just representing ice dynamics along a single line, that flow line in red that you see here. Okay, so this is an equation that's trying to capture all the stresses acting on the ice sheet. We have, first of all, the longitudinal stress, which is caused by the ice expanding and contracting as it flows. We have the basal shear stress, which is caused by friction between the ice and the bed. And then we have the driving stress, which is a result of gravity acting on the ice. So all of these things are acting on the ice sheet at the same time. and ice flows according to this balance of stresses. Now, the key issue here is that a lot of terms in this equation we don't have complete knowledge about. So it's difficult for ice sheet models to actually realistically capture what happens in real life because we don't have perfect knowledge of how fast ice flows, or we don't have, perfect knowledge of friction underneath ice. Over many decades, Antarctic scientists have worked to collect data all over the continent. So in the quantities that I just listed previously, there are some that we are more certain about and some that we are uncertain about. One that we have reasonable knowledge of, reasonable observations of, is the surface elevation. So we know roughly how high the surface of ice is all over the continent relative to sea level. Since 1985, there have been a number of satellite missions that tries to measure the surface elevation of ice. And these are basically satellites like the one that you see in this little image here. This is ICESat-2. It's a satellite that flies over the surface of the Earth, sends a light beam down to the surface of the ice, waits for that light beam to come up, and based on timing, based on measuring how long it takes for that light beam to come back up, we can measure the distance between the satellite and the ice, and then work out the surface elevation of the ice. Okay, now this plot on the right-hand side here shows the change in elevation, the average change in elevation per year from 1985 to 2023. And these blue areas are basically where the ice is gaining in height, and red areas are areas where the ice is decreasing in height. So you see that there are areas where we're losing ice badly, particularly in these two glaciers here, which are Pine Island Glacier and Thwaites Glacier in Antarctica. We will be applying our methodology to Thwaites Glacier in a couple of slides, so I just wanted to point out that's where Thwaites Glacier is. There are areas where we're gaining ice as well, but overall there's a net loss in ice over time. Okay, we also have reasonable amount of data for the velocity of ice. So this is a map of the ice velocity. And you see in the middle of the ice sheet, there are all of these dark blue areas here. This is where ice is very slow flowing. So it flows at a rate of maybe a couple of meters a year. And then as ice flows towards these outlets, it picks up in speed. And then these colors become redder and redder, and the velocity becomes roughly a couple of kilometers a year. Even then, that's quite slow compared to anything else we can think of. So ice is a very, very slow flowing fluid. The good thing is we have high resolution data of the velocity all over the continent. The data can be as high resolution as 120 meters. And we also have continuous coverage in the sense that we have the velocity data every year. Now, it's relatively easier to measure what's going on at the surface of the ice compared to what's going on underneath. And one of the things that we are uncertain about is the bed topography under ice. You can imagine how difficult it would be to measure the underlying bed, which is vast and inaccessible. So when I started my research in 2021, BedMap2 was probably one of the most comprehensive data sets of the Antarctic bed. And this plot here basically shows you all the flight lines where we have data, where we have measurements of the bed elevation. Okay, so we have these aircrafts that fly over the continent and then send radar waves that penetrates through ice. And then when it hits the bed, it reflects back. And again, based on measuring how long it takes for those radar waves to go to the bed and back, we can measure the bed elevation. So we have bed measurements along these flight lines, which are in reality quite sparse. This color scale basically shows you the distance between flight tracks. And so there are some areas where we have dense measurements and some areas where we have no data. This is an area where there are no observations within 500 kilometers. Okay, this was BedMap2. And then 2 years ago in 2023, BedMap3 came out, and a number of these data gaps have been filled. But still, there are areas where there are no measurements of the bed within a 100-kilometer radius. So we have measurements of the bed, it's just sparse. And I do need to say that BedMap regrids these observations to a half-kilometer by half-kilometer grid using interpolation. Just to give you an idea of how sparse the measurements actually are, 93% of the values in this map, this is a map of the topography of the bed, 93% of the values are interpolated. So we have knowledge of maybe 7% of the continent, and then the rest is estimated. And then this interpolation method doesn't actually make use of ice sheet models to account for the ice dynamics when it fills in the gaps between observations. Okay. Then another thing that we're uncertain about is the amount of friction between the ice and the underlying bed. So friction is part of the base of shear stress that's holding ice pack from flowing into the ocean. And when I say friction, I actually mean this friction coefficient, which is really a mathematical quantity that lumps together a lot of things. It lumps together the hydrology, the way water flows between the bed and the ice. It lumps together how hard or soft the bed is, how deformable it is, and how rough it is. All of these things are lumped into a number. And it's not easy to measure this either in real life or in a lab setting because it's difficult to simulate all of these conditions realistically. So we don't have any direct measurements of friction. What usually needs to happen is that we need to use the quantities that we have reasonable knowledge of in order to estimate what we're uncertain about. And the hope is that if we obtain better estimates of what we're uncertain about, then we can better calibrate these ice sheet models and help them capture reality better. And then in turn, that's going to help us improve sea level rise projections. It's hopefully going to help us narrow down the uncertainty in our estimates of how much sea level is going to rise. All right, now that I've set the scene, I'm going to show you our proposed method of estimating subglacial conditions using deep learning. What is deep learning in the first place? Deep learning has been a very active area of research over the last decade, and the cornerstone of it is the neural network. Deep learning uses a neural network to model the relationship between some input and output. You've probably heard of the famous handwriting recognition example, where we try to get a neural network to recognize handwritten digits and then tell us what number it is. In order to train a neural network, we need to give it a lot of input data. This is called training data. We just give it a lot of zeros. And with every of these corresponding zero, we have a corresponding output. So we tell the neural network that this is a 0, and then this is a 1, this is a 2, and so on. Then we get the neural network to make its own predictions. And at first, it might think a 0 is a 2. And by comparing what the neural network outputs and the expected output, we can then tune the neural network. So you can think of this neural network as like a mathematical machine with a lot of knobs and dials. And based on the output that this network gives and the expected output, the difference between that, we can turn these knobs and dials a little bit at a time until the neural network can accurately recognize that a 0 is a 0, a 1 is a 1, and so on and so forth. Okay, and then the process of learning in deep learning really is just the process of tuning the parameters, these knobs and dials within that neural network. And once we are done training the neural network, we can give it data that it hasn't previously seen. So it might have seen a lot of 7s before, but it hasn't seen this particular 7. And we hope that based on all the training process, based on all the 7s it has seen before, it would recognize the features that make a 7, and then tell us, hey, this digit is actually 7. Okay, that's the idea behind deep learning. Now, in the same way that we can train a neural network to learn to recognize handwritten digits, we can train a neural network to look at the ice conditions at the surface and then make a guess as to what happens underneath. In particular, in this case, our input is not going to be handwritten digits. It's going to be how high the ice is at the surface relative to sea level and how fast it is flowing. And then the output instead of the number is going to be what's the bed elevation underneath the ice and how much friction between the ice and the bed. Now, the bed elevation is usually spatially varying, so it varies along this horizontal flow line, and usually it's the negative. The neural network to be able to output this. How do we do that? Well, step one, we're going to have to generate a lot of training data. We're going to have to generate a lot of handwritten digits, if you will. So for a given bedrock and friction, we can use an ice sheet model to simulate the evolution of an ice sheet. Okay, so bed and friction are the input to an ice sheet model, and the output is going to be like this image that you see here, where we have the ice sheet beginning from this outermost curve, the darkest one, and as the ice evolves in time, it retreats from the ocean, and that's what you see in these fading curves here. So you can simulate the evolution of an ice sheet in time, mathematically. And we can do this for a lot of combinations of friction and bedrock. So if we think friction is going to be like this and the bed looks like this, then it's going to give us a corresponding ice sheet profile, ice sheet evolution. We can do this for many variations in the friction and bed. For every variation is going to output a little bit, an ice sheet that is a little bit different, okay? And this then becomes the training data for our neural network. Okay, this is called the forward process, where we put friction and bed into the ice sheet model and we output the surface conditions. We do this 50,000 times, so you can think of this as like 50,000 handwritten digits, if you will. Right. In order for the neural network to understand this training data, it would be better to represent this evolution in terms of the spatial temporal images or Hofmöller plots. So we're just representing the information on the left-hand side here in a different format. Here you have the surface elevation of the ice, which is high in the middle of the ice sheet. It's more than 1 kilometer high. And then as the ice flows towards the ocean, it goes down. It decreases in elevation. And that's what you see here in this middle plot, where we have high surface elevation at the beginning. That's the dark blue area. And then it goes down, 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 down towards zero as the ice flows to the ocean. And so every row here in this square plot shows the evolution of the ice in 1 year. And we have 20 years of evolution. A similar thing happens with the velocity, but kind of in the opposite way. So we have very slow flowing ice in the middle of the ice sheet. And as ice flows to the ocean, it picks up in speed. We see that pattern here where we have close to zero velocity at the beginning. And as we move to the right, the velocity increases and we see the color getting redder and redder. Okay, so we represent the ice sheet's evolution as these images that show the surface elevation and velocity in space and in time. Now, I also need to say that there's subtle patterns going on here that's going to differentiate one ice sheet from another, and that's going to help the neural network sort of distinguish between what bed and friction corresponds to what surface elevation and velocity. Okay, so this is our training data. We have pairs of friction and bed profiles, and this corresponds to specific surface elevation and velocity. And so we have 50,000 pairs of these input and output, and we train a neural network to learn the inverse problem, where this time we give the neural network what we know at the surface. These are the surface elevation and velocity, and we get it to infer the relationship between what's going on at the surface and what's going on underneath. Okay, so that's the reverse process. And then once the neural network is done training, once it's learned the correspondence between what's going on at the surface and what's going on underneath, we can then give it data from an actual glacier, data that it might not have seen before. And then we see what it says about the underlying subglacial conditions. Now, at this point, I want to pause a little and talk about what we actually expect to see from the neural network, because it's a little bit different from the handwriting example where you just get a number from the neural network. I'm going to begin a little bit further back when we were generating data. So when we generated data, we actually need to make some assumptions about the likely range of friction and the likely range of bed elevation. Okay, so we assume initially that friction is likely to lie within a certain range. This is not an actual plot of friction, it's just a graphic to represent like our initial estimate. So we say that friction is on average going to be around the blue line, but it can vary in between the blue shading. This is what we call the prior distribution of friction. Okay, and we're going to update this prior estimate of where the likely ranges of bed and friction are using data which are surface observation. So this is what happens in Bayesian statistics, which is really the machinery that underlies the neural network that we're using. And by updating our prior understanding of the bed and friction with data, we obtain something called the posterior distribution, which is where we believe that the bed and friction are likely to be, given what we've observed. And so what the neural network is really trying to do is it's estimating a whole distribution, actually. It's estimating not only where the average value of friction would be, but also a range of plausible values. And with this range comes associated probabilities. So we're saying that it's most likely going to be around this red line here, but it can also plausibly be in between the red shading. Maybe more likely here than up here, for example. Okay, so we don't just get a single guess, we get a guess with uncertainty around that guess. And with that, I'm going to show you actual estimations of friction in bed from a simulation study. Sorry, that was just explaining the posterior and prior in words. So again, the prior distribution is where our initial estimates of the range of likely values of bed and friction are, and the posterior is what we're really trying to estimate through the neural network. Okay, so these are the estimates from a simulation study. Simulation study means that this is an experiment where we know the true answer. We know the true friction and we know the true bed. And it's like a sanity check to make sure that the neural network is able to accurately estimate these values, just to make sure that it's doing its job. Okay, so in this case, we know the true friction and is plotted as this black line here, and the true bed is plotted as the red line. And then the neural network estimates the friction is plotted in red, and also for the bed. You can see that the neural network, the red line is following the black line quite closely, which shows that the neural network is doing a good job at estimating the friction and also the bed topography. In particular for the bed, the red and black lines are almost overlapping. And the reason it's doing so well here is partly because we do have sparse observations of the bed, which are these black dots here that helps constrain the neural network estimate. Okay, I also want to point out that the red shading here is the uncertainty. So we're saying not just that friction is on average going to be where the red line is, but also that we get a range of uncertainty estimates around that guess. So there's higher uncertainty here on the left-hand side, and that uncertainty kind of narrows down as we go towards the right. And we postulate that this is because in this area of the ice sheet, the velocity is very slow. And it picks up as we flow towards the ocean. So it's easier to estimate friction when the ice is flowing more rapidly than where it's effectively not flowing. Okay. I also want to point out that this blue line here is estimation results from the ensemble Kalman filter, which is another method in the literature. To date, I think it's the only method that tries to solve the same problem, while also taking into account ice dynamics through an ice sheet model. And we just want to show here that the neural network predictions achieve better accuracy than the ensemble Kalman filter, which is the best we've got in the literature at the moment. Okay, now that I've shown you an overview of our methodology, I can then show you how we apply this to an actual glacier in West Antarctica. So we're applying this to a glacier transect in Thwaites Glacier. This is a glacier that has been rapidly losing ice, and the idea to our experiment here is to take a point in this glacier and then infer the bed elevation and friction along this flow line. Okay. Now we have observations of surface elevation along this flow line from the years 2010 to 2020, and we also have sparse measurements of the bed elevation along this flow line from the BedMap 3 dataset. You can see that these are fairly sparse measurements, but it does give us an idea of where the bed is going to be initially. So again, we're going to begin by generating lots of training data. We assume that there's an average level of friction along the flow line, and then there are variations along that average level. So here it's about 0.02 of a nasty unit that I really don't want to pronounce. And we generate these friction profiles through a Gaussian distribution, okay, with some assumed mean and some assumed covariance function. For the bed, we do have observations to constrain our initial estimates. And so we generate these bed profiles using Gaussian processes or Gaussian process regression, which you can think of as the clever method of taking a pencil and then connecting the dots. Okay. Once we have 50,000 different variations in bed and friction, we plot them through an ice sheet model and generate the evolution again of many corresponding ice sheets. And then you get these spatial temporal images here of what's happening at the surface. Now, the challenge with working on a real data application is that in reality, we have a reasonable amount of missing data. And when we do have data, the data tends to be noisy. In particular, for the surface elevation, we generally have data for where the ice is grounded when it's resting on the bed, but not where the ice is floating. So over a portion of the flow line, data is missing. And then for the velocity in the initial years from 2010 to 2012, we have a lot of missing data in parts of the flow line. And where we do have data, it is extremely noisy. So we have very high velocity in one spot, very low velocity in the next, and then it goes high again, low again. And it's very unphysical in that way. So when we generate training data, I'm just showing you the velocity in subsequent years, actually. So in 2016, we do get somewhat better data, but it's still noisy in parts, and same with 2019. So when we do generate training data, we need to take into account that in reality, we have a lot of missing data. When we generate training data from the model, it's going to be a complete map of the surface elevation and velocity. There's going to be nothing missing because this is a model that we can control. But if we train the neural network on this, it's not going to know what to do when it encounters actual missing data. So when we're generating examples for it to learn from, we also have to make the examples mimic what happens in real life. And we do that by basically masking out areas in the training data where we don't expect to have real data. Okay, so wherever ice is floating, that's basically from 150 kilometers onwards to the ocean, we just set the surface elevation to 0. And same with the velocity. Okay, so we apply these missing patterns to training data in order to make it mimic the behavior of real data. And then we can give all of these masked training data to the neural network and get it to learn, again, the relationship between what's happening at the surface and what's happening underneath. And then once training is done, we can give the neural network actual data. So these are actual images of the surface elevation and velocity from that flow line in the glacier that I showed you earlier. And then we see what the neural network has to say about the underlying bed and the underlying friction. Okay, so these are the neural network estimates. In this case, we don't have anything to compare estimates to because there's no ground truth. So we compare the neural network estimates against another data set called bed machine. The neural network estimates are in red, along with uncertainty in red shading. And then the bed estimates from bed machine are in blue. Now, bed machine is another data set like bed map, but the method that they use to map the bed is slightly different from the interpolation method by bed map. I'm not going to go into details on that, but you can ask me at the end if you want. The point is we have another data set called bed machine to compare our estimates to, and in general, we do observe that the neural network estimates are in good agreement with bed machine, except for one area where there's a difference. Now, for the friction coefficient, we do get an estimate of the average level of friction and then some uncertainty around that level, but we don't have anything to compare it to because there's just no measurements of friction. So how do we check that our estimates are reasonable? Well, we do what statisticians call posterior predictive checks, where based on the likely range of values estimated by the neural network, we generate possible variations of what the bed looks like. That's the red lines here, and friction as well. And then with that as input, we put those through an ice sheet model and then try to simulate an ice sheet. And what should happen if the bed and friction are well estimated is that the ice sheet model with those as input should produce ice geometries that are similar to real life. Okay, so we're trying to basically make the model replicate reality well. And so when you simulate from the ice sheet model using these bed and frictions that are estimated from the neural network, you get this red shading here on the right-hand plot. And the actual observations of surface elevation and velocity are these black lines. And you see that when the ice sheet model is calibrated with input from the neural network, it generates observations, these red shading that captures reality well. Now, these blue lines here in the background are our prior samples. They are basically what our initial estimates of the bed and friction before any training with the neural network went on. And you could also just plug them through an ice sheet model and see what the model output looks like. And that comes out as these blue shading here. Now, the blue shading you can think of as the output from an uncalibrated model. And the red shading is the output from the calibrated model, calibrated with estimates from the neural network. And the story is that once the model has been calibrated with better estimates of the bed and friction from the neural network, it can then match reality better than when it was uncalibrated. Okay, that's the story here. And I'm showing you 2012, 2015, and 2018 with similar stories, but you can do that for all the years from 2010 to 2020. Okay, what we can also do is out-of-sample forecasting. So you can train the neural network on only the first 10 years of data from 2010 to 2019. You leave out the very last year. And once the neural network is done training, you can use the estimates of bed and friction from the neural network to predict what goes on in the very last year. Okay, and then you can compare that to actual observations. So the right-hand side plot here is basically showing that. The model output is the red shading, and actual observations are the black lines. You can see that even though the actual model had no data from 2020, it can capture what happens in 2020 well. Okay. Very lastly, I want to point out the connection between what we do and the estimation of sea level rise. So our output, the estimates of bed and friction, can be used to work out the volume of ice that will contribute to the ocean. So floating ice actually doesn't contribute to sea level because it's already floating, it's already displacing water. The part of ice that really contributes to sea level is this area where the ice is grounded when it's resting on bedrock. And that's why the bed estimation is necessary for working out the volume of ice that can raise sea level. Now, a part of this is actually already resting in seawater. So the yellow part effectively doesn't contribute to sea level. with some caveats. Right, the part of ice that actually contributes to sea level is the blue area here, and we call that the volume above flotation. That's calculated as this whole colored area, the blue and yellow, and then minus this ice volume that's already resting in water with some density adjustment because there's a difference in the density of ice and water. Okay, so you can work out this volume above flotation, and if we see this volume above flotation going down, then that means ice is losing volume. That volume is going to the ocean, and then sea level is going up. Okay, now I'm going to show you a plot of the volume above flotation, a box plot where we show the median volume above flotation from 2010 to 2020 based on our model, based on our calibrated model. And the story is that the median level of volume is going down, which shows that ice is flowing into the ocean, and that's going to raise sea level. Oh, that disappeared just then. Now, we do get some uncertainty estimates around this volume above flotation. And as the years go on, we get increasingly uncertain about how much the glacier is losing ice. That's why you see these boxes and these whiskers widening in range. Okay, but the overall message is that Twiggs Glacier is losing ice, which is getting increasingly uncertain about how much it loses exactly as the year goes on. Then the sea level contribution is basically this change in volume above flotation divided by the area of the ocean. So when you do volume divided by area, you get the change in height, and that's how much sea level changes. Okay, so the estimates of the bed and friction that we get will help calculate the sea level contribution from an ice sheet. So just to tie everything up, we've developed a deep learning approach for estimating Antarctic subglacial conditions, namely the bed elevation under ice and also the amount of friction between the ice and the bed. This approach is physically consistent because it uses an ice sheet model to account for ice dynamics in time. And there are many ways that this research can be extended. We can first of all train the neural network on more glacier and ice sheet geometries so that it can be generalized to more areas of the ice sheet. And we can also make use of more realistic ice flow models, those in 2 dimensions and 3 dimensions, that can simulate the evolution of ice, not just along a line, but also over an area or in 3D. And then once again, the estimate from our method is really just the first piece of the puzzle. So they feed into calculations of sea level contribution. And our hope is that with better estimates of subglacial conditions, we can reduce uncertainty in sea level rise projections, because as you can see, every centimeter of sea level rise matters. Thank you.